Welcome to your deep dive. Today, we're going to kind of unpack a 1995 research paper. And it's kind of cool because it revisits like this classic algorithm, the Kernighan-Lin Search, or KLS.
Oh, wow.
It's used to solve really, really tricky problems like figuring out the best route if you have multiple stops.
Ah,
Kind of like what those mapping apps do.
right.
Or designing the circuits in your phone.
Mm.
And the cool part is, the author Ali Dazdan is actually looking back at his own work from 30 years ago.
Oh, wow.
So by the end of this deep dive, you'll not only get how this algorithm works, but also see how really clever ideas can last a long time.
It's amazing how these totally different problems, trip planning and circuit design, they share a common approach.
Right.
And it's all thanks to Kernighan and Lin. The Kernighan and Lin search tackles these combinatorial optimization problems where you're trying to find the best solution out of just so many possibilities.
Yeah, so how does KLS actually work? It's got to be super daunting to find the best solution when there are just so many options.
Okay, so imagine you're trying to find the lowest point in this huge hilly landscape. A simple way would be to just walk downhill.
Okay.
This is like a hill climbing algorithm. You just keep going down until you can't go any lower. But you can imagine you might get stuck in a valley that's not the absolute lowest point.
Yeah, you might miss out on an even deeper valley somewhere else.
Yeah.
So how does KLS get around that?
The Kernighan-Lin algorithm uses this thing called a variable depth search. So instead of just taking the immediate downhill step, it'll explore a bunch of moves, even uphill ones.
Right.
So it's like the algorithm is saying, let me check out a few different paths before I decide. This way, KLS can escape those those valleys that look like the lowest point but aren't, and it can find a better solution overall.
Oh, that's smart. So how did Dazdan actually, evaluate how well this performs?
Well, he tested KLS on a bunch of problems, like a standard set.
Okay.
The kind that researchers were using in the 90s to benchmark algorithms, like genetic algorithms. Those were becoming pretty popular back then.
Yeah. These problems had different challenges, like
Yeah.
how many variables are involved, or if the solution space is smooth or all jagged.
Okay, so it wasn't just the basic KLS, though, right? He actually made some specialized versions, KLS-1 and KLS-2.
Yeah, Dazdan realized that sometimes if you know something specific about the problem, you can really improve the performance.
What?
Like KLS-2, for example. Okay. It actually used the fact that some problems have symmetrical solutions, which made the search go a lot faster.
Wow, so how did these specialized versions stack up against, all the others? Did they find better solutions?
KLS wasn't always the fastest in terms of computer time,
Okay,
but it did find really great solutions in a reasonable time.
okay.
And the surprising thing is that KLS-2, the one that used that symmetry trick, that one consistently gave some of the best results,
Right.
even beating out some of those really complex algorithms.
So even though all this research is from back in 1995, it seems like the core ideas are still relevant today. Yeah, for sure. Dassin actually mentions this in his paper. He says this work might be like an early example of how useful KLS really is. And people are still doing research on KLS today.
Okay.
So that says a lot about its relevance.
Yeah. No, I'm definitely starting to see why this algorithm has lasted so long. But before we get too far, I want to take a step back and really look at those specialized KLS versions, KLS-1 and KLS-2. What did they add and how did that change their performance?
Well, KLS-1, that was designed to handle problems with integer coefficients.
Okay.
So, it knows that the solutions have to be whole numbers. It seems pretty simple, but it didn't always make it work better.
So why wouldn't that always be helpful? Why wouldn't knowing that always make it better?
Well, it kind of shows something important about designing algorithms. Just adding in any random information isn't enough. It's got to be the right kind of information used in the right way.
Okay.
Sometimes only using integers could actually make it harder for KLS-1 to look around the solution space and find the best one.
Gotcha. So what about KLS-2? What kind of symmetry did it use?
A lot of these optimization problems, especially the ones about dividing things up like graphs, have symmetry in them.
Okay.
Imagine you're splitting a network into two equal parts.
Okay.
You could swap those parts, but the solution is basically the same.
Right.
KLS-2 was made to see that kind of symmetry and use it.
Okay.
That way, it didn't have to search as much and could find a good solution faster.
So it's like knowing the structure of the problem gave KLS-2 a real edge.
Yeah.
To get a better feel for how these algorithms work, can you give us an idea of the problems that Dazdan actually used to test them?
He used a set of like standard test functions.
Okay.
They're used a lot in optimization research.
Okay.
These functions were like landscapes with different levels of like how complex they are.
Okay.
Some were smooth and predictable, like rolling hills.
Okay.
But others are all rough and you don't know what's coming, like a mountain range.
Can you give us some specific examples of these test functions?
Sure. One is called Rosenbrock's saddle. It's shaped like a saddle,
Okay.
with this long, narrow valley leading to the minimum. Algorithms that just go downhill can get stuck there easily.
Right.
But KLS, because it has that variable depth search, can navigate that tricky landscape and find the real best solution.
So it's like if things outside the box or outside the valley. What about a function that's even harder?
Well, there's Shekels foxholes. That one's famous for being really complex.
Okay.
It's got a bunch of valleys, all different depths. Makes it really hard to find the absolute lowest point.
Yeah, like imagine trying to find the deepest point in the Himalayas.
Exactly.
You might think you've got it, but there could always be a deeper one somewhere else.
Right.
So how did KLS do with that tough one?
Well, it didn't always find the very best solution,
Okay.
but it always found pretty good ones. Even for like really fancy algorithms that function super hard,
Yeah.
it just shows how tough these optimization problems can be.
These test functions really help us see the challenges that these optimization algorithms have to deal with.
They do?
And they show us the strengths of KLS, like getting out of those local optimas and exploring all those complex landscapes.
Definitely. Dastan's work gives us a great look into the world of optimization algorithms and how they've changed over time. And it shows us how important KLS still is.
Yeah, it really is amazing that a technique from 1995 is still relevant and can compete with the newer approaches. What are some things we can take away from Dastan's work, even if we're not computer scientists?
I think there are some good insights here, even if you're not, super into algorithms.
Right.
One big takeaway is that even in a field like tech where things change so fast, the basic ideas and, the really good solutions, those can stick around for a long time. Like the Kernighan and Lin algorithm, it shows that sometimes the classics are classics for a reason.
That's kind of comforting, isn't it? Like,
Yeah.
it doesn't always have to be about chasing the newest thing.
Yeah. And another takeaway is how important it is to know the specifics of the problem. Dastan made those special versions of KLS, like KLS1 and KLS2.
Right.
And that shows how if we really understand the problem, we can tailor our approach and maybe get much better results.
It's like that saying, use the right tool for the right job. Like a one-size-fits-all approach doesn't always work best.
Right. And Dastan's research also shows how problem solving is like an ongoing thing. He looked back at his own work after 30 years.
Yeah.
And that gave him a new perspective, new insights. It shows that learning and improving, that never really stops.
It's pretty cool how a simple idea from so long ago can still affect how we deal with tough problems today. This has been a really fascinating deep dive into the Kernighan-Lin algorithm.
It really has. It shows how powerful those simple solutions can be, how important it is to know the specifics of the problem, and how we never really stop learning and discovering new things and problem solving.
So keep exploring, keep asking questions, and keep looking for those elegant solutions. You never know where the next big breakthrough is going to come from.